Today we'll see the topic related to sampling theorem. We all know how to convert a continuous time signal into discrete time signal, and we know the importance of discrete time signal and where we are using discrete time signals. So basically, we are using sampling theorem to convert a continuous time signal into discrete time signal. In this lecture, we'll see the importance of sampling theorem, representation using impulses, Fourier transform of a sample signal, signal reconstruction, signal interpolation, aliasing, multi-signal processing. So representation of a continuous time signal using impulse function. So how we are representing a continuous time signal using impulse function. So basically we are converting continuous time signal into discrete time signal by multiplying our continuous time signal with train of impulses. So we know how to represent train of impulse. So here is the formula to represent our impulses. Train of impulses. Sigma n equivalent to minus infinite to plus infinite, delta of t minus nts. So if you vary the value of n from minus infinite to plus infinite, you will get infinite number of delta function which is spaced by t duration. So basically, here the goal of this lecture is to convince you that band-limited continuous time signals, when sampled properly, can be represented as discrete time signals with no loss of information. So to convert a continuous time signal into discrete time signal, we are using sampling theorem. So to avoid aliasing, so we will get the aliasing effect while reconstructing our signal back to our original signal. So if you want to reconstruct our original signal, always keeping one condition, that is what fs is greater than or equal to 2fm. So why we are keeping that condition, we will see in the following lecture. And first of all, the condition to take the signal is, first we need to take a band limited continuous time signal. We should not send the signal as it is. We should band limit it by passing through a filter. Okay, so this remarkable result is known as sampling theory. So we are reconstructing our original signal with no loss of information. So that is what your sampling theory. We can represent our signal x of t, which is the combination of discrete time signal. That is what x of t should be multiplied by train of impulses. So here is the formula. A sample version of a continuous time signal x of t is x suffix s of t, which is equivalent to x of t multiplied by p of t. So x of t is your original signal and we are multiplying it with the train of impulses. So already we have represented p of t in terms of delta function. So if you solve it, you will get a del sigma n equivalent to minus infinite to plus infinite x of nt delta of t minus nt. So this is known as idealized sampling. We can derive the complex Fourier series of a train pulse. So this is the Fourier transform of your train pulse, which is equivalent to sigma k equivalent to minus infinite to plus infinite ck e power j k omega naught t. Here omega naught equivalent to 2 pi by t. So whereas ck formula is 1 over t integral minus t by 2 to plus t by 2 p of t e power minus j k omega naught t dt. So already in place of p of t, we are replacing it with delta of t. So delta of t has some properties there: multiplication property, convolution property, number of properties are there for delta of t. Here we are using multiplication property. If your x of t multiplied by delta of t, the resultant you will get as what? X of 0 delta of t. That is what your multiplication property. With that property, the delta of t power minus j omega naught t will be converted as simple delta of t dt, whereas integral over delta of t is nothing but unity. So that is the reason here we are getting the value which is equivalent to 1 over t. So finally, we can write the formula for P of t, which is equivalent to sigma k equivalent to minus infinite to plus infinite 1 over t e power j k omega naught t. So how can we write the Fourier transform of a sample signal? So already we have sample signal which is equivalent to x suffix s of t, that is what P of t multiplied by x of t. So already we know what is P of t, what is x of t. Now if you replace your P of t, that is what sigma k equivalent to minus infinite to plus infinite 1 over t per j k omega naught t, which is multiplied by x of t. So with the help of Fourier transform properties, we have number of properties related to Fourier transform. Based on the modulation property, we can rewrite this formula as 1 over t sigma k equivalent to minus infinite to plus infinite x of here x of t is multiplied by e power j k omega naught t. So it is in time domain. If you convert it into frequency domain, so definitely we can write it as x of omega minus k omega naught. So that's what we are representing here. So let us represent our x of t in frequency domain with a triangle which is band limited to minus b to plus b. So here is our signal. Now you are multiplying your x of t with train of impulses, so that finally you are getting the equation which is in frequency domain, that is x of omega minus k omega naught. So you are getting infinite number of frequency spectrums which are delayed by omega naught duration. So here is our resultant signal. So this is omega naught is very important here. Yeah. Signal reconstruction. How we are reconstructing our original signal. How we are reconstructing our original signal. So already you have transmitted your signal through a filter and you have converted it into band limiter signal. Now the band limiter signal is passed through a circuit. There we are keeping sampling theorem. Means what? We are sampling our input signal with the help of train of impulses. Okay. Now we need to reconstruct the signal by transmitting our signal, by multiplying our signal with the help of train of impulses. In frequency domain, we are getting train of spectral version of your input signal. Okay. Now if you want to reconstruct your original signal, so definitely we need to transmit the modulated signal or sample signal through a filter. Okay. So here the filter must be an ideal filter with the upper and lower limit, that is what, minus b to plus b, so that you can reconstruct your original signal as it is. But practically ideal filters are not exist. Here the sampling frequency omega is equivalent to 2b, which is referred as Nyquist sampling frequency. There are two practical problems associated with this approach. So one is ideal filter should not. Ideal filter should be physically realizable because it has cutoff frequency. It should have cutoff frequency from minus b to plus b. And the second one is the input signal is typically not band limited. See, we need to band limit our signal from minus b to plus b. So practically how we are doing it, we are transmitting our signal through a filter. That filter may be ideal filter or practical filter, but ideal filters does not exist. So definitely we will go for practical filter. In practical filters, you won't get short the cutoff frequency, that is what minus b to plus b. Okay. So it is very difficult to reconstruct our signal by passing it through a low pass filter which have cutoff frequency p. See, here is signal interpolation, the frequency response of the low pass filter. So already I told you the transfer function of our low pass filter should be, your filter should be in the range from minus b to plus b with some amplitude. So here I'm keeping that amplitude equivalent to t, and this is what your h of t, which is in time domain. Now if you multiply your h of t with excess of t, that is what, again you are transmitting your sample signal through a filter. So the resultant is what? Convolution of sample signal with the function, transfer function of your system. So if you do this, definitely you have to get the resultant signal, which is the original signal, but practically it is not possible with the help of ideal filters, because ideal filters are not realizable. We need to go for practical filters, whereas the practical filter should not have short cutoff frequencies. So this is what the problem what we are facing in the reconstruction of our original signal. So definitely we need to keep a filter which is practical, and the sampling frequency should be greater than 2 FM. Why? Because if your sampling frequency is more than 2 FM, so there is a space between every two spectrum of your input signals, so that you can reconstruct your original signal with the help of practical filters itself. Aliasing. So I already told you, while reconstructing our original signal, definitely we will face a problem, and the problem name is aliasing. So what is aliasing? If your Fs sampling frequency is equivalent to 2 FM or less than 2 FM, so definitely there is a problem. If it is equivalent to 2 FM also, it is very difficult to reconstruct our original signal, because ideal filters are not possible. We can't reconstruct the ideal filters. And the second one is, if your Fs is less than 2 FM, if your Fs is less than 2 FM, so there also we will get a problem. That problem is what? Those two spectrums will overlap. So because of that overlapping, we will miss the original information. Okay. If the signal is not band limited, distortion will occur when the signal is sampled. We refer to this distortion as aliasing. This is about the sampling technique. So to reconstruct our original signal, we need to keep our fs which is greater than or equivalent to 2fm. Okay. In time domain, we are fixing ts value, sampling period value, which is less than tm by 2, so that we can avoid aliasing effect.